Let me start with a question that sounds almost ridiculous the moment you say it out loud. We live in a galaxy with roughly 400 billion stars, and we now know that most of those stars have planets. Do the math, and you end up with a Milky Way that probably holds more worlds than there are grains of sand on all the beaches of California. On top of that, the universe has been around for over 13 billion years. That's an unimaginably long stretch of time for life to appear, evolve, and for at least one civilization to figure out how to build a rocket and come say hello. So why hasn't it happened? Why is the sky so quiet? Why hasn't anyone knocked on the door? By the time we're done, you'll see why the distances between stars aren't just big, they're brutally, absurdly, almost comically huge. And you'll also see why the laws of physics, real physics, not movie physics, make it extremely unlikely that any alien creature will ever park a spaceship on your lawn. I'm not asking you to take this on faith. I'm going to use numbers, the kind nature actually uses. So let's begin with something you already understand. You've probably been on a long road trip. Maybe you've even driven from Los Angeles to New York. That's about 3,000 miles. If you push hard, you might do it in 3 days. You get tired. You stop for gas. You eat a sad sandwich at a random roadside place. Even though it's only 3,000 miles, it feels like a serious journey when you're the one doing it. Now here's the move that changes everything. The nearest star to our sun, Proxima Centauri, is about 4 light-years away. 4 light-years sounds manageable until you translate it into normal distance. 4 light-years is roughly 25 trillion miles. Let that land. If you took that Los Angeles to New York drive and stacked it end to end, you would have to make that trip about 8 billion times to cover the distance to the nearest star. 8 billion coast-to-coast trips just to reach the closest neighbor. And that neighbor is practically sitting in our lap compared to most of the galaxy. At this point, someone always says, "Okay, but we wouldn't drive. We'd use a rocket." Fair enough. Let's do rockets. The fastest thing humans have ever built and sent into deep space cruises at around 40,000 miles per hour. That sounds fast because it's fast on Earth. But at 40,000 miles per hour, how long to Proxima Centauri? Around 70,000 years, not 70, 70,000. 70. That's longer than all of recorded human civilization. We've only been writing things down for around 5,000 years. To make this trip, you'd need a mission that lasts 14 times longer than the entire history of writing. You're great, 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 and you'd have to repeat great about 2,000 more times. Grandchildren would be the ones arriving, if the ship still worked, if anyone was still alive, and if anyone still remembered why they left in the first place. This is what people miss when they casually say, "Space is big." It's not just big. It's so huge that the word big starts to feel useless. It's a kind of emptiness the human mind wasn't built to picture clearly. We evolved to worry about immediate dangers, not to grasp the scale of the gaps between stars. But let's be generous. Maybe aliens are smarter than us. Maybe they've built far faster ships. Fine. Let's give them an incredibly generous speed, say 10% the speed of light. That's about 67 million miles per hour, wildly beyond anything we can do. At that speed, the trip to Proxima Centauri still takes about 40 years. 40 years inside a cramped machine, racing through the coldest, emptiest, most hostile vacuum imaginable, just to reach the nearest star. And that's only the beginning. If they wanted to travel to somewhere closer to the middle of the galaxy at that same speed, the trip would take around 1,000,000 years. One way, no return ticket discount. But let's not stop there. Let's push it harder. Suppose they can do half the speed of light. Now we're talking about something that sounds almost magical, and this is where the universe stops being romantic and starts being violent. At half the speed of light, every tiny grain of dust in interstellar space becomes a weapon. A speck the size of sand hits with the energy of a grenade, and space isn't perfectly empty. There's thin gas out there too, roughly 1 or 2 hydrogen atoms per cubic centimeter. At half the speed of light, those atoms turn into a relentless stream of radiation, like standing in front of an X-ray machine that never turns off. Papers have been written on this. The calculations show that even at 10% the speed of light, radiation from interstellar hydrogen alone would be about 60 rem. A lethal dose for humans is around 500 rem. In other words, without extreme shielding, you'd be dead very quickly. At higher speeds, it gets worse. To survive, you'd need shielding meters thick made of something dense, which adds mass, which demands more fuel, which increases mass again, and the spiral keeps tightening. These problems don't show up one at a time. They stack and amplify each other. The faster you go, the more energy you need and the more shielding you need, which adds mass, which demands even more energy. Physics pushes back from every direction, and even if you somehow managed half the speed of light, crossing the galaxy still takes about 200,000 years. That's within a single galaxy, one out of hundreds of billions in the observable universe. So the real situation is this: the distances aren't a minor inconvenience. They behave like a wall built into reality itself. And the rule that turns that wall into something truly unforgiving is the speed of light. Let's talk about why the speed of light matters so much, because this is where people get confused. They imagine it like a speed limit sign on the highway, 55 miles per hour, and if you push it to 56, you just risk a ticket. That's not what this is. The speed of light isn't a rule somebody invented. It's built into the geometry of the universe. Einstein showed that space and time aren't separate categories. They're woven into a single fabric, and the speed of light is like the exchange rate between distance and time. When you try to go faster and faster, something strange happens that feels like science fiction, but is solid science. Time slows down for you. Your momentum becomes harder and harder to increase. In everyday terms, people often say mass increases. And the key idea is that as you approach the speed of light, it becomes infinitely difficult to accelerate further. The closer you get, the more energy you need, and as you approach the limit, the energy required blows up without bound. You can't just build a better engine and break through, because the universe doesn't charge a bigger fine. It simply doesn't allow the crossing. It's not that we lack the technology. It's that physics says no. Now someone always raises the obvious counter, okay, but what about warp drives? What about wormholes? What about bending space? Sure, speculation is fun. It pushes imagination and sometimes points to real ideas. But we have to separate fun ideas from physics you can actually rely on. A warp drive, for example, comes from a set of equations published largely as a mathematical curiosity. In principle, those equations describe a way to compress space in front of a ship and expand space behind it, so the ship rides a ripple in space-time instead of moving through space in the usual way. It's a beautiful concept. The trouble is what the equations demand to make it work. They require a form of energy with negative mass. Not negative charge, negative mass. We've never observed anything like that. We have no experimental evidence it exists, and there are strong reasons to think nature doesn't permit it in the way a warp drive would need. That's not an engineering challenge. That's hoping reality contains a hidden ingredient we've never seen. Wormholes have a similar problem. General relativity allows solutions that resemble tunnels through space-time, like shortcuts, but the wormholes we know how to write down are either unstable, meaning they collapse before anything could pass through, or they require exotic matter with negative energy density, which is the same basic issue in different clothing. We don't have it. We don't know how to make it. And there are strong theoretical arguments that stable, traversable wormholes may not be possible at all. The universe appears to dislike shortcuts. So, here's the reality check, as plainly as I can put it. Stars are astonishingly far apart. The fastest possible speed is the speed of light, and you can't even reach it because it would require infinite energy. Even at large fractions of light speed, travel times are measured in decades, centuries, or longer, and the environment between stars becomes actively lethal. And we do not currently have real, testable physics showing a reliable way around these barriers. That's where we stand. Now let's make the situation even tougher, because so far we've mostly talked about distance and speed. We haven't really faced the energy bill. Imagine you want to send a real spacecraft to another star, not a tiny chip, not a single atom, a useful craft, maybe even with people on it, or at least heavy equipment that can actually do something when it gets there. Let's say the ship has a mass of about 100,000 kilograms, roughly like a loaded Boeing 737. Not absurdly huge, a modest interstellar boat. To push that mass to just 10% of the speed of light, you need on the order of 4x 10, 23 joules of energy. Those numbers are so big they become meaningless unless you compare them to something real. The total energy output of all human civilization in a year Every power plant, every car, every factory, everything comes out around 5x 1020 joules. So to accelerate one modest ship to 10% light speed, you're looking at roughly 1,000 times the entire yearly energy output of the whole human race. One ship, one trip, one way. And that's before you deal with the nastiest part of space travel. You have to carry your fuel. This is where the rocket equation becomes tyranny. Fuel has mass. That mass needs fuel to push it. That extra fuel adds even more mass, which then requires even more fuel, and the numbers can explode. With chemical rockets, the kind that took us to the moon, the amount of fuel needed to reach even 1% of the speed of light becomes so large that the math turns absurd. It isn't just impractical, it becomes physically ridiculous. People then say, okay, so use better fuel. Fine. Imagine nuclear fusion, one of the best realistic energy sources we can picture in the foreseeable future. Even then, the fuel-to-payload ratio for a trip to the nearest star at a decent speed is enormous, often thousands to one. You end up with a fuel tank like a skyscraper for every passenger. And if you want to slow down when you arrive, you need fuel for deceleration too, which doesn't just double the problem. Because of the exponential nature of the rocket equation, it can make the whole thing dramatically worse. You can point to antimatter as the ultimate fuel. Matter-antimatter annihilation converts mass into energy with perfect efficiency. It's the most energy-dense fuel you can imagine. But there's a catch. We can only produce antimatter in tiny quantities at huge cost. If you added up all the antimatter humanity has ever produced, it wouldn't even heat a cup of coffee. To launch our modest ship to another star, you'd need tons of antimatter, tens of tons. Where does that come from? No one knows. It certainly isn't sitting around waiting for us. Now pause and think about what this means for aliens. People often assume that if a civilization is advanced enough, problems like this simply disappear. They wave a hand and say, they'll have technology we can't imagine. But physics isn't a local rulebook. The speed of light doesn't increase because a species has better politics. The rocket equation doesn't become kinder because a civilization is older. E-MC2 doesn't negotiate. Physics is universal. That's what the word universal is doing there. So when someone tells me aliens have visited Earth, I have one simple question. How? Not how in a poetic sense. I mean, show me the propulsion. Show me where the energy comes from. Show me how they dealt with radiation and dust impacts and decades or centuries of travel. Show me how they carried fuel or avoided the fuel problem entirely. Because until those questions have serious answers, the idea of routine alien visitors isn't just unproven. It clashes hard with everything we currently understand about the universe. This brings us to a famous moment in scientific history. A lunch conversation in the summer of 1950 at Los Alamos. A group of physicists were walking to lunch, joking about flying saucers. Among them was Enrico Fermi, one of the sharpest minds of the 20th century. In the middle of the joking, he suddenly asked a question so simple, it silenced the table. Where is everybody? What Fermi realized was both obvious and unsettling. The galaxy is extremely old. Our sun is middle-aged. There are stars billions of years older than ours. If life can appear on planets, and if intelligence can evolve, then somewhere in the Milky Way, civilizations should have arisen billions of years before us. And with even a modest head start, say 1 million years, such a civilization might have had time to spread widely. Even traveling slowly, even at 1% of the speed of light, you can cross the galaxy in about 10 million years. 10 million years sounds huge to us, but compared to the galaxy's age, over 10 billion years, it's a blink. There has been plenty of time for someone to go everywhere. And yet we don't see it. No confirmed signals, no probes, no artifacts, no unmistakable engineering projects, no visitors. The sky is quiet. The solar system looks empty. The galaxy, as far as our observations can tell, shows no clear signs of being colonized or even visited by an advanced civilization. That tension between what seems possible in principle and what we actually observe is what people call the Fermi paradox. It's one of the deepest questions in science because it forces you to confront both astronomy and biology, both physics and the behavior of life. There are several major categories of answers, and many of them are uncomfortable. The most direct possibility is the simplest. Maybe we are alone. Maybe intelligent life is so rare that among 400 billion stars, we're the only species that ever built a radio. That sounds arrogant until you look carefully at the evidence we do have. A famous way of thinking about this is the Drake equation, proposed by astronomer Frank Drake. It isn't a physics equation so much as an organized list of unknowns. You take the rate at which stars form, multiply by the fraction with planets, multiply by the number of planets that could support life, multiply by the fraction where life actually starts, multiply by the fraction where intelligence evolves, multiply by the fraction that develops detectable technology, multiply by how long such civilizations last. The result is an estimate of how many detectable civilizations exist in the galaxy right now. Here's the problem. We don't know most of those numbers. We've gotten better at the first few. We know roughly how many stars form each year in a galaxy like ours, on the order of 1 or 2. We know that most stars have planets. We're improving at estimating how many planets sit in a habitable zone where liquid water could exist. These early terms are encouraging. There could be billions of potentially habitable worlds. Then you hit a brick wall. What fraction of habitable planets actually develop life? We don't know. We have exactly one example: Earth. One example tells you almost nothing about probability. It's like flipping a coin once, getting heads and trying to calculate the odds from that single flip. You can't. Then, what fraction of planets with life produce intelligence? Again, we only have one example. And even on Earth, intelligence took about 4 billion years to show up. For most of Earth's history, life was just microbes, single cells, no brains, no eyes, just chemistry working in water. Intelligence is not some guaranteed destination. Evolution doesn't aim at it. Evolution experiments, and most of what works is bacteria. In fact, if you look at Earth's full history, one fact stands out sharply. Life has existed for nearly 4 billion years. Out of the countless species that have come and gone, exactly one has built radio telescopes. That isn't a trend, it's a fluke. Timing matters too. Even if civilizations do arise, they have to exist at the same time to notice each other. The galaxy is more than 10 billion years old. A technological civilization might last 10,000 years, maybe 1,000,000 years if it's unusually stable. But even 1,000,000 years is still a tiny slice of galactic time. It's like 2 fireflies blinking in a field the size of a continent. Most blinks never overlap. Most civilizations that ever existed may already be gone, and many that will exist might not be born yet. We could be in the right place, but the wrong era, or the right era, but in the wrong neighborhood. The universe doesn't coordinate schedules for our convenience. This is why the Drake equation can produce almost any answer you want. If the unknown fractions are generous, you get millions of civilizations. If they're harsh, you get a number far less than 1, meaning we're likely alone. The Drake equation isn't a calculator that spits out a firm result. It's more like a mirror. It reflects your assumptions back at you. Now consider another possibility. Suppose intelligent civilizations are not rare. Suppose they arise often. Then the silence becomes a different kind of message. Maybe civilizations don't last long. This idea is dark, but it has logic. Look at us. We've had nuclear weapons for only a short time in the span of history, and already we've created the ability to destroy our own civilization. We've come frighteningly close to doing it. How long can a species hold that kind of power without using it? 100 years? 1,000? 10,000? No one knows. But it's not unreasonable to think many civilizations invent the tools of self-destruction before they build the wisdom to avoid using them. And it isn't only weapons. A civilization could poison its environment, collapse its ecosystems, trigger runaway climate changes, burn through essential resources, or create conflicts it can't contain. It could build machines that outcompete or replace it. There are many paths to collapse, and the more you list, the more plausible the idea becomes that civilizations often end themselves quickly, at least on cosmic timescales. There's also a useful way scientists think about civilization scale: how much energy a civilization controls. One idea, associated with Kardashev, describes three broad levels. A Type 1 civilization uses the energy available on its planet. A Type 2 harnesses the full output of its star. Imagine surrounding a star and capturing most of its light. A Type 3 taps into the energy of an entire galaxy. The reason this matters is not because it's a cool label. It matters because energy use leaves fingerprints. Thermodynamics is not optional. Any civilization that uses large amounts of energy must dump waste heat. So a Type 2 civilization should be detectable in principle, not because we'd hear their radios, but because a star enclosed by a massive energy collecting structure would look strange. It might be dim in visible light, but bright in infrared as it radiates heat. We've surveyed huge numbers of stars looking for that kind of signature. So far, we have not found a clear case, no strong confirmed example that survives careful analysis. And a Type 3 civilization would be even harder to hide. A galaxy shaped by vast engineering projects would show abnormal infrared patterns. We've looked at galaxies too. They look like galaxies, no obvious sign of cosmic scale industry. This leads to an idea that many people find chilling: the Great Filter. The basic claim is simple. Somewhere between lifeless chemistry and a galaxy-spanning civilization, there is a step that is extremely hard to pass. Something filters out almost all life before it becomes widespread and obvious. The unsettling question is where the filter sits. Is it behind us or ahead of us? If the filter is behind us, that's good news. It means the hardest steps were things like the origin of life, the leap to complex cells, the rise of multicellular organisms, or the evolution of intelligence. We already made it through. The sky is quiet because almost nobody else ever got this far. That would make us rare. Not because we're chosen, but because we beat staggering odds. If the filter is in front of us, that's very bad news. It would mean that many civilizations reach roughly our level and then fail again and again before they spread into the galaxy in a visible way. It would suggest we may be approaching a cliff that we don't yet see, and that most who came before us went over it. We don't know which is true. Nobody does. But the silence is real, and it should make us think carefully about what kind of future we're building. And if there's one practical takeaway from all of this, it's not that the universe is empty. It's that if life is rare, or fragile, or short-lived, then what we have here is unbelievably valuable. Whatever happens next, we probably can't count on rescue from the stars. If we want a long future, we'll have to earn it.